Hey, so today I'll talk a little bit about Taylor dispersion and Brownian motion. I have done some small simulation and there's a link in the description below where you can download it and play around with it on MATLAB. So Brownian motion is the random movement of particles in a fluid. This happens mainly because of collisions from the particles in from the molecules in the liquid that cause this particle to move in a particular direction. Even though if you see in the bulk the fluid is not moving, but the particles inside it are moving at any temperature above zero as per kinetic theory of gases. And that's why they cause collisions and these dust particles or any of these particles then just move. So now I'll talk about Einstein's equation of diffusibility, which gives you the diffusion coefficient or diffusibility of any particle in a particular fluid. So D is the diffusivity or how easily one material can move into another material or diffuses into another material. And it's given by the expression which states kBT, that's the random motion or the thermal motion upon 6 pi mu r. Mu is the viscosity of the fluid and r is the size of the dust particle. So the Fick's first law of diffusion, it states that the flux is directly proportional to the concentration gradient and the chemical potential. This is used to describe how many particles pass over, or the flux or the number of particles that pass over a given area in a given time. The Fick's second law of diffusion gives a relation between the time and the displacement or the position of the particles. So D is the diffusivity again here, and this is analogous to the heat equation and has good solutions that can be obtained. Basically, after any given time, it tells you how much distance the particle has traveled. The solution of this is given as follows. This is for an input of a delta function. A delta function is when you inlet everything, all the material in at any given point, at any given space and point. You just inlet everything. For our convenience, we take it as time and space quantity equal to zero. That means at just any given moment, everything is just injected at one particular point, and you just see how everything distributes. Funnily enough, it distributes as a normal or a Gaussian, which is one of the most easily and well understood distributions in mathematics, where for a given space and time, we can find the concentration and we can obtain points from a Gaussian at any time, which could correspond to a random kick due to Brownian. So now I've simulated a simple random walk. The link is in the description below for the M file. You can play around with it, and if you want, you can change the diffusivity, you can change the time step and see how the kick takes place. Brownian motion, and you'll obtain a normal distribution at any point if you take the histogram of it. But I'm going to talk about what the given position is at a given time. Basically, it is the given position at any time can be defined as the given position in the previous time plus a kick in the random direction. So this is what a random walk is generated. You can see that there is a time step and a position. As the time is increasing, you can see that the particle is moving in any direction, up and down in one direction. Basically, it goes up, then it goes down. It just varies in any direction that you can see. So each random kick that is obtained from a Gaussian, which talks for a given diffusivity of the particle. So now we talk about advection diffusion. Advection diffusion is when there is a bulk velocity apart from the Fick's law of diffusion. So if you put velocity equal to zero, you will get back the original Fick's law of diffusion. But when you do have a velocity, how is the behavior of these particles? So to solve this, what I've done is I have first taken the position of the particle at any given time. You can do that. You can do that as the position of the given particle at any time plus is equal to the position at the previous time plus the velocity into a time step plus the random kick or diffusion that takes place, which causes another movement for it. So again, I've attached the M file in the description. You can change the velocity, you can change the diffusivity, and you can see what happens. You can change the time step and you'll be able to get some amazing results. Let's start in a case where we have extremely low velocity. So you can see that the Brownian motion is quite dominant. The red is the baseline if you assume that there is only a velocity and there is no Brownian motion, the particle will tend to travel in that sort of a path. But you can see that because of the random kicks, the particle has a tendency of traveling in a different way, and there is Brownian motion that is dominant. Now, if you increase the velocity, you can see that the trend starts becoming closer to the baseline of how the case should be. That is, the velocity is starting to dominate the effect rather than Brownian motion. You can see it's becoming even lesser, and when we increase the velocity, you can see that they just collide. That means in this regime, Brownian motion is so less that all the change in position is only due to the drift velocity or the velocity in the bulk. Now I'm going to talk about quasi-flow. Quasi-flow is a very interesting phenomena. Quasi-flow is the solution to a incompressible fluid that is Newtonian in a circular cross section like a pipe when the flow is laminar. Basically, the flow is slow, steady, and the viscosity does not change with time or space. So when you solve the solve the Navier-Stokes equation and put the no-slip boundary condition, you get the following expression, which is a parabolic distribution with respect to the pipe. A no-slip boundary condition is the one where the velocity at the wall or the velocity of the layer just above the wall is the same as the velocity of the wall. So if the velocity of the wall is zero, you'll get a nice parabolic profile that you can see below, which varies as r square. And r is the radius of the pipe, capital R. Quasi flow, and you can see the parabolic pathway. So this is the solution to the Poisson flow, and it is useful in determining many other quantities. Talk about what Pecklet number is. Pecklet number basically gives you a ratio between the diffusion due to bulk motion and the diffusion due to just the regular gradient transport or Brownian motion or the random kicks of the diffusion. So this is a ratio that is used to tell us what is the dominating factor, and with the higher Pecklet number, it tells you that the advection is the dominating factor, and lower Pecklet number tells you that diffusion is the dominating factor in the transport or the movement of. So last, I'm going to talk about what Taylor dispersion is, which was first invented or found by, not invented, which was first found by G.I. Taylor. So when you have an inlet or this is also like a delta function, when you have all your inlet of a pollutant or something that is undesirable or a solute particle which could be desirable, and you have a quasi flow, so there is a tendency of these particles to follow the quasi flow because that's how the velocity is. When this happens, you can see a parabolic shape of the particle as well. But then you can see that there are local concentration gradients that come into the picture here and here as compared to here and here. So these particles tend to come in the inside, and these particles tend to spread outside. And over time and space, you can see them spreading out to form like a plug of the pollutant, and with time this plug is continuously spreading like a Gaussian. So this phenomenon is called the Taylor dispersion and has many application in microfluidics and biomedical engineering. So that is my presentation. Thank you so much. There is a link in the description below for all the major topics, and there is also the M file that I've attached. Thank you so much.